Hello everyone and welcome back to this next lecture. So in the previous lecture we had built up the schematic of this boost converter and we had run the simulation to get this particular result. So in this lecture I'm going to analyze these results and I hope you also have taken a moment to actually browse through these results and see what we get. So first thing we're going to do, we're always going to go and verify whether the gate voltage is indeed legit. So for that I'm just going to go and just multiply this by 0.1 so that we can at least scale this. And here you can see very clearly we are still applying the same ramp to our duty ratio. So the duty ratio is gradually increasing from 0 to 0.5 and I'll talk about this very soon, the significance of this particular thing. So if you go and have a look at this, you will see that our actual pulse width modulation is perfect. We are starting our pulse at the beginning of every switching cycle and the pulse is going back to 0 or rather minus 10 or whichever value we've chosen when the duty ratio becomes less than the carrier voltage, right? So this is all perfectly okay. And the entire duration of a particular switching cycle is exactly 100 microseconds, which is what we wanted. So now that we are done with this, let's go back and zoom. So let's look at our output voltage and let's look at our input voltage. So our input voltage is way below. Actually, this is not very nice color combination. So let me change this to red. Okay. So the input voltage is now red and the output voltage is green or whatever color this is. I don't know. Anyway, so it's now very clear they're different. The input voltage is around 12. Let me put this grid back again. The input voltage is 12, which is exactly half the equidistant between 10 volts and 14 volts. And look at the output voltage. It is close to 22 volts, which is at least almost double the input voltage. So let's go and zoom in. And this is what we're getting. Right? So it is, you would have expected 24 volts because after all, the duty ratio is 0.5. And if the duty ratio is 0.5, then we are expecting double the output voltage, rather the output voltage to be double the input voltage. But as always, as I said, there are resistive drops in the circuit, and in this case, in our case, the most biggest drop is of course the resistance here, right? You can always play with this resistance, try to bring it down and see for yourself what you get. There is also this diode and therefore you can also try to change the resistance of this diode. You can always go and look at the pertinent help file page. You will see here there are parameters and there must be a parameter such as the series resistance, right? And there are many other parameters that you can also find. So this I will leave to you as an exercise. Now let's go ahead with our analysis. We have seen that this is fairly okay. It does seem like the boost converter is working. I would recommend you to change the duty cycle. So, or rather the duty ratio, not the duty cycle, the duty ratio to some other value and verify for yourself that the output voltage is exactly as desired. That is, it conforms to that equation of 1 upon 1 by d, 1 minus d, which is the expression between the output voltage and the input voltage, right? So now let's come over here and have a look at this input. So I'll come over zoom and we can also at the same time zoom in to our capacitor voltage because we should also check out where it increases and where it decreases. So I'll just zoom in here as well. Fortunately, I'm just not able to zoom enough. Okay, that seems okay. So now let me put in the grid here and the grid is on. So you can see that when at the beginning of a cycle, actually I probably haven't chosen very nicely, but anyway, you can see when the gate pulse is going low and the power device stops conducting, then in that case the inductor current begins to fall. And the reason for that, as we've already seen, is that this is when the inductor current and the input voltage are now supplying power to the output voltage, output capacitor. And that can be seen by the rise in the voltage across the output capacitor. The output capacitor is not increasing, is increasing from its value at the beginning of this transition to the end of the cycle. And when the gate pulse is high, which is when the power device is conducting, the exact opposite happens. The inductor current rises because the inductor is storing energy. from the input and the output voltage is decreasing because the output voltage is disconnected from the input. Remember, the diode is preventing the output capacitor from discharging through the device, because if without the diode, the output capacitor would have been short circuited by the power device. And because of that, the output capacitor is supplying the load resistor, and therefore its voltage will decrease. So this again shows that our simulation is kind of in line with our theory. Now, the last one is, of course, this is a comparison of the output voltage and the inductor current in the same particular graph. You can just verify this for yourself. It is merely the same analysis which I did before. So this shows that our buck boost converter seems to be working in exactly the manner we expected to. There are certain issues, like for example, where are we losing 1 volt? That is of course an issue, and you should investigate it. You can always decrease the resistance of the inductor or the series resistance with the inductor in order to see if that decreases this particular drop. I will leave this to you as an exercise. I will stop this lecture now, and in the next lecture I'm going to talk about one other issue, and that issue is with respect to this startup time. Let me just zoom in again, and you'll see here that we had raised the duty ratio from 0 to 0.5 rather than applying directly 0.5. We had seen this also when we were actually simulating the buck converter, and we saw that simulating, or rather introducing such a ramp in the duty ratio, reduces in lesser initial transients. And you see, there are no initial transient, at least there is no current going completely out of bounds. But in this boost converter, this becomes extremely important, and I'll talk about that in great detail in the next lecture. So if you did not get these results, you got something else, or you are trying something else and you think those results are wrong, post in the Q&A forum and I'll do my best to help you. Otherwise, in the next lecture, we will talk about the initial conditions. Thank you so much for listening, and goodbye for now.